So in this we are going to investigate if the principle of least time is really equivalent to Snell's law. So according to Fermat's calculations, the principle of least time is equivalent to Snell's law, and traditionally that's what is thought during refraction of light especially. So this is a circular refracting media with uniform refractive index mu. So this is a circle with radius r. We can consider the center of the circle as the origin, and this is the refractive index of the ambient media, mu naught. So this is the source of light P, which is given by the coordinates minus r minus a. Uh, so the light originates from here, and this is the ray destination. This is one of the points where the light ray originating from here reaches after some time. So according to the principle of least time, whatever path the light takes between P and Q, that has to have the least time. The path should have the least time. So according to the principle of least time, light ray potentially evaluates all possible paths, some random path like this. It will consider all these paths from P to Q and chooses the path which takes the least time. So in this sense, it's like if as if light is conscious, and its present course of action depends on future space-time events. So it's a teleologic principle. It depends on the future. The present depends on the future. It's not like causality. Uh, but according to Snell's law, sin I by sin r equals constant, mu by mu naught, or sin r equals sin I into mu naught by mu, where I is the ray of incidence angle. So it's measured with respect to the uh, normal to the direction of the interface at that point, and r is the refraction angle. So we are trying to imagine a simple situation where only one of the two statements, one of these two statements, that principle of least time or the Snell's law, only one of them can be true. So we're trying to imagine such a simple situation here. And also one consequence of the Snell's law is like that if mu equals mu naught, then sin r becomes sin I. So that is r equals I. So this implies that light travels in a straight line in a homogeneous media. So light traveling in a straight line is just a consequence of Snell's law if we consider like this. And when I equals 0, r is also 0. This implies that light travels in a straight line across the media if the angle of incidence is 0. Since both the principle of least time and Snell's law imply a straight line path within a homogeneous media, we shall just consider such paths which are piecewise linear like this. So we take so within a media from this point P to x1 y1, it is a straight line, and when the media changes, the direction of the ray might change. So we have this another random point x2 y2, so it travels from here to here, and then it finally joins Q. So we'll consider piecewise linear paths like this and evaluate which has the least time. And also while doing these calculations, we exclude paths around the media interface, these boundary passing through these boundaries like this, which always involve unwarranted turns in the path. Even though it can be piecewise linear, we will not consider such paths. So in principle, we are not actually considering many of the random paths. So this actually should give an idea that principle of least time may not be true in a most generic sense. So in a limited sense, let's try and see if it works. So in order to go from P to Q in those piecewise linear paths, this is the kind of time we get in terms of these variables. So for example, this is the time related with the first segment from P to x1 y1. So the speed of light here in this media is c by mu naught, where mu naught is the refractive index of the media and c is the speed of light in vacuum. So and this is the distance within the square root, this x1 plus r plus a whole square plus y1 square. This is the length of this segment divided by the speed of light c by mu naught gives the time the light takes to cross this segment. Similarly, this is the time taken on this segment. Here the speed of light is c by mu, because mu is the refractive index of the media, and so on. So this is the third time taken on the third segment. So we can note that due to the constraint in the problem, this x1 y1 and x2 y2, these 2 points lie on a circle. So they have to satisfy this equation, x1 square plus y1 square equals r square, where r is a constant, which is the radius of the circle, and x2 square plus y2 square is also r square. When we use these two equations of the circle and eliminate y1 and y2 using these equations from the time equation, we end up with this format. So this is what the when we eliminate y1 and y2, this is what we get. And further, in order to find the stationary points, or the least time path, or the maximum time path, we consider this partial differential of time variable t with respect to x1 and x1 and x2, sorry. So we have eliminated y1 and y2 from these equations. Only two independent variables are there now, x1 and x2. So we take partial derivatives with respect to that. So finally what we get after doing this is we get the condition that x2 must be equal to minus x1 and y2 is equal to y1. So basically we end up paths which are symmetric about the y-axis like this. So these are the kinds of paths. One of them will have a least time path, but this is the first condition we get, that they have to have this kind of a symmetric path over the y-axis, which is basically coming out because of the basic symmetry in the posing of the problem itself, as we can see. So further we can use this triangle formed by this triangle. This alpha is the angle at which the light ray is emerging from the source. Alpha plus theta is the angle of incidence at this point, and theta is the angle of refraction. This is because this path is symmetric about the y-axis, so we are considering those paths, and we have this triangle, and in this triangle these are the kinds of relationship we get, and we can express theta completely in terms of r, a and alpha, and using these things, just from these triangle relationships, we can find the length b in terms of r, a and alpha. So one of the advantages of this form is that, say at alpha equals 0, this becomes a singularity, or 0 by 0 form, which is indeterminate. So when we convert it to this form, we can see that it doesn't have that 0 by 0 form. It evaluates neatly to, at alpha equals 0, b becomes a, or just a, which is what we expect when the straight line is like this, when the ray is going like this, b equals a. Otherwise b is always greater than a. So this is the time needed for the light to travel along this path, some random path like this with alpha plus theta incident angle. So this is what we get. So when we eliminate the b from this equation, from this time equation, we'll end up with a term like this, ct by, where we have multiplied t with some constants c and r divided by 2 into r plus a. So essentially this represents time, and this is the equation. This is what the equation reduces to. So in order to find the maxima and the minima points, we will take a differential of this term with respect to alpha. So alpha is the only variable here. This mu is constant, r is constant, a is constant. R is the radius of the circle, and a is the minimum distance of this point from one of the circumference points of the circle. So when we do this, we'll end up with three factors. This d by d alpha of this term has three factors. So sin alpha is one of the factors. So if this is 0, one of the possibilities is sin alpha is equal to 0. It can be 0. So in that case, we get a straight line path passing right through the center of the circle diametrically from P to Q, like this, the straight line in red. The other condition we get either sin alpha is 0 or this factor can also be 0, but this implies that a equals 0. This is the only condition in which this becomes 0. This LHS becomes 0 only when a equals 0. But we are considering the situations where a is non-zero, where a is situated a little bit away from the circle. So this is, by the design of the problem, we are considering a greater than 0. So this is not a valid solution for our case, for our situation. And the other possibility is this expression can become 0. So these are the three factors multiplying by which we get this LHS of this d by d alpha. Either sin alpha can be 0, or this can be 0, or this can be 0. So we are considering this now. So when this is 0, what do we get? So this, from this triangle we get this relationship. When we put it into this factor, so we end up with expression like this, which can be further much simplified to a form like this: sin alpha plus theta by sin theta equals mu by mu naught. So this is what is implied. So this is actually Snell's law. And from the triangle we can also see that this sin alpha plus theta by theta should be equal to this ratio of these two distances, r plus a and b. So this part, these two terms form the Snell's law, and these two are coming from the triangle. So this is what is Snell's law. So we are getting the Snell's law directly from the principle of least time, which is what is expected in many situations. So of the two possible solutions, so now we are ended up in a situation where we have two possible solutions: either alpha can be 0, or this condition is 0, which implies sin alpha plus theta by sin theta equals mu by mu naught. So there are two possible solutions. Obviously, I mean, they both can be a minima, or so let's see which of them is a minima or a maxima, or what's happening here. So as we discussed, this d by d alpha of this time term t is made up of three factors: this a, b and c. So if we do take a second derivative of this term, time term, with respect to alpha, d square by d alpha square of this, we get an expression like this, because it's a product of three terms. And at a equals alpha, or sin alpha equals 0, or a equals 0, when this first term is 0, first factor is 0, these two terms drop off, because a equals 0 at this point. Alpha equals 0. So we'll just consider this factor at this point, alpha equals 0. So we end up with an expression like this, which evaluates into this a by r plus a into whatever written here. So and this is the solution it represents, the solution which is going right through the center of the circle, which is alpha equals 0. So on converting, so this is what the expression we get finally: d square by d alpha square equals a by r into mu naught into 1 minus a mu by r plus a mu naught. So in this case we know that the first derivative is 0 in this case, because a equals 0. This first derivative, d by d alpha of this time factor is 0. And the second derivative, if a mu is greater than r plus a mu naught in here, if a mu is greater than this, then this second derivative becomes negative. So if the second derivative is negative and the first derivative is 0, then at that point we have a maxima. So under this situation, the time taken along this path is a local maxima. And if a mu is less than r plus a mu naught, then this d square by d alpha square, this second derivative becomes positive, so it becomes a minima at that point. So both these cases are possible. This solution can either be a maxima or a minima, depending on the value of mu with respect to the geometry and the refractive index of the ambient media or the outside media. So now let's consider the second part of the solution, when c equals 0. So this works when the same situation when a mu is less than r plus a mu naught. So we put c equals 0. So again we see that this term where c appears and this term where c appears, these two terms are not important, because they value to 0. So the only term left is a into b dc by d alpha. So that gives an expression like this when you finally simplify: minus mu a square b square. So this will always be less than 0. So the first derivative is 0 and the second derivative under the situation c equals 0 or this term is 0 always gives a maxima. So this solution is a local maxima solution, time maxima. So consider so under this situation where mu is less than r plus a mu naught by a, we get a minima solution when the time is minima or the least if it travels right through the center, this straight line path, or we get a maxima solution when it takes this path which is symmetric about the y-axis. So this path, if it takes, then it's a maxima. So it has both, there is one minima path and a maxima path according to these equations. And we see that light travels along this both these paths. And also, okay, we'll see why this a mu is less than r plus a mu naught when a equals 0. So when c equals 0, when c equals 0, or when alpha is not equal to 0, we know that mu by mu naught equals r plus a by b. That is what we got in the previous page. If we see, this is the ratio we get: sine alpha plus theta by sine theta. From the triangle we get this: mu by mu naught is equal to r plus a by b, and b is always greater than a by construction. So therefore mu by mu naught will always be less than r plus a by a. So that is why this condition when c equals 0. So these two are the same condition, and we know that that means that when mu is less than a certain upper limit, we get one maxima and one minima and a maxima solution. There are two paths possible, and light takes both these paths. So more specifically, this is the situation, this is the condition we need when mu is above this certain minimum value and below this minimum value, we get both these solutions. So it's actually principle of stationary time rather than the principle of least time. That is what has to be considered in general. So principle of least time is already not as valid. We can see in the simple circular solution that it's actually it must be actually the principle of least time or stationary time. Principle of least time is already broken here in the simple case of reflection through circle, because it takes this path, upper path, not going straight to the center. There is another path possible, and this is a local maxima, local time maxima. So both the maxima and minima possible. So later it was thought that okay, it's not principle of least time, it must be principle of stationary time. So we will show even that is broken. So okay, this is what we got. This is the Snell's law: sine alpha plus theta by sine theta equals mu by mu naught is Snell's law, and this being equal to this is from the triangle construction. So from this we get one single expression for theta in terms of a, r and alpha. So theta can be completely expressed in terms of alpha here. So plugging this back into this equation, we get mu equals mu naught divided by cos alpha square root of this factor. So this means whenever when as mu increases, as the refractive index of the media increases, as mu increases, the alpha decreases, the angle from which the ray is emerging from the light source in order to pass to Q, that angle alpha decreases. So it has a reverse relationship. So from this equation we see that when mu is the lowest, so this is the lowest value allowed when this path forms, the upper path. So when mu equals mu naught r plus a by divided by a into 1 plus 2 r by a, the alpha is maximum. So this is alpha max, which is the case of the tangential solution. So this is the tangent from this point to the circle. So this is the maximum alpha possible, and this happens at this refractive index. So this is the low, at the low end, when the refractive index of the media is low, we have high alpha values, and when the mu or the refractive index of the media is high, when it is equal to mu naught into r plus a by a, this solution collapses to this. Now Actually, as the mu keeps increasing, this the upper path keeps reducing its height, keeps reducing, and it collapses to this central uh, path passing through the center of the circle at the high mu value. So this is alpha equals 0. This is the lowest alpha value, and this is the highest alpha value possible. So basically it means that, and for some value in between these two extreme values of mu, we get an in between path like this. So basically when mu is between these two limits, we get two distinct paths. One is this upper path and one passing through the center, and above this limit or even below this limit, we find only this central path. We will not find any other path, but within this limit, when mu is between these two extremes, we find two different paths. One is the maxima path and the one is the minima path. So basically, if the refracting media is homogeneous, the principle of stationary time is valid even with complex geometries. We can change this geometry to many complicated forms, and we'll see no matter what complex geometry we take, this principle of least time being equivalent to Snell's law comes up, and principle of stationary time. So both the principle of stationary time and the Snell's law are equivalent in whatever complex geometries we call, but that gets broken when the refractive index is variable within this media. So for example, we saw the relationship between mu and alpha in the previous week. That was actually for finding alpha at which the path p to q, the stationary time path is formed, the alpha corresponding to this mu, but we can use this equation to have a variable refractive index path. So at whatever alpha, so if this alpha is say 45 degree, we put that in, we have a certain number associated with that, the refractive index. So if that is the right amount of refractive index that is there, then according to the Snell's law, it should pass through that. So when the light ray appears here, it if it has the right amount of low refractive index according to this formula at this point locally along this line, so it should travel along this according to the Snell's law, and whenever it encounters the mid region, if it is the right amount, it will just turn and complete this path p to q, so on. So according to Snell's law, all these multiple paths should be possible. Actually infinitely many paths satisfy the Snell's law when we have the right amount of variation of this refractive index. So at each of these points locally, the Snell's law is satisfied. It comes here, sees the refractive index is this value, low or high or whatever, and it turns by the right amount and completes this path p to q. So let's see. So this was the time factor that we had used earlier. So here mu can be either constant or variable. So we'll plug in this variable value now here because we are considering the variable solution. So okay, here also we are considering all these paths which are symmetric about the y-axis. All other paths will give much higher times. So this solving this should be enough for this case also. So we'll consider only these paths which are like symmetric about the y-axis. So after plugging in this variable mu, variable refractive index, this is what the expression we get for the time. And differentiating that, we this is the factor we get, and from this we see that alpha equals 0 is the only place where this first derivative becomes 0, and at that point there is a minima, there is a time minima. So alpha equals 0 is this straight line path passing through the center, this bottom one, p to q, the straight line path, and this happens to be also the least time path according to this equation. So if the least time path is correct, this should be the only path that the light should take from p to q, this one, the straight line path. But if Snell's law is correct, then it can take all these infinitely many paths at different heights because it encounters different variable refractive index at different points according to this equation. So according to the Snell's law, not only the least time path which happens at alpha equals 0, but all the other paths up to alpha equals alpha max are possible. So between the central path and the tangential path, all the infinite paths in between, they satisfy Snell's law, but only one path, the central path, satisfies the least time principle or the stationary time principle. So this experiment definitely can decide between which of the statements is true, whether principle of least time is true. If we do this experiment and find only the path PQ is selected, none of the other paths are present from P to Q, then the principle of least time is correct. But if all the other paths are also, all these infinite paths are also possible, that's happening in physically when we do the experiment, then principle of least time is wrong, because PQ is the only least time path. All the other paths have higher time than Q, this straight line PQ. So this experiment can definitely decide between whether the principle of least time is correct or the Snell's law, which is applied locally at each point, is correct. So in all likelihood, the Snell's law is correct from the physical intuition that we see, that when the light ray encounters here, comes here, when the light ray comes here, it encounters some low refractive index, or it comes here, it encounters some medium level refractive index, and when it comes here, when it is a high refractive index, all these paths will be selected according to the Snell's law, and most likely that will work. So variable refractive index breaks the principle of least time. That is, when we do the experiment and see all these paths are possible, then we see that the principle of least time is broken. It can be done in the triangle also. In the triangle, the direction of variation will be reversed. The low mu values will be here and the high mu values will be here, higher refractive index. Basically here alpha increases with increasing mu. In the other path, alpha decreases with increasing mu. And also here, when we do the time derivative, when we find the stationary points, we find that there is a condition for the maximum time path. There is no minimum time path, the maximum time path, and the light passes through that, which is okay, which is like the one of the stationary points. But according to Snell's law, it does not only pass through this maximum time path, but it also passes through all the other paths, alpha to alpha max. There are infinitely many paths. So it can be done both in any shape. It can be done. So we are just shown for triangle and a circular shape. So one of the consequences of these having these infinitely many paths is that if we are standing at Q and observing this at various different angles, the light originating from Q will come to Q from P. The light originating from P will come to Q in various different angles, and when we look back at various different angles and project the ray back, we will find that the object at P, this point-like object at P, will be extended throughout this vertical green line passing through P. So in all these places, in all this vertical line, we'll see P. So when we look at this angle at this point, we'll see that P is actually situated here. If we look at this angle, it's obviously we'll see P is situated here. When we look at this angle, we'll see that P is situated somewhere on top. So this whole vertical line, green line, will show up as P. The object is present all over this place. So that's one of the consequences of this. Okay, that's all for now. Thank you. So basically this shows that the variable refractive index breaks the principle of least time.